hybridization. So when you start to look at these bonds, you start to realize that in order for a covalent bond to form, we need one lone unpaired electron in a given orbital on one atom to bond with a lone pair or a lone unpaired electron on another atom in its own orbital. If you look at a molecule of carbon, carbon's electron configuration is 1s2, 2s2, 2p2. So since it has two unpaired electrons here in its 2p, we'd expect carbon to form two bonds. But in reality, what we're going to see is that carbon forms four bonds, which means that essentially what has to happen is one of those 2s electrons has to get excited. And it has to jump up into a 2p to open up. We know that requires energy though. At that point, carbon would have four open electrons, one in the 2s and then three in the 2p, where it could form two bonds. But the big problem is that those four atomic orbitals would not be able to bond and make the shape that we know carbon would make when it forms four bonds, which is a tetrahedral. CH4 makes a tetrahedral, right? So in order for carbon to make its proper four bonds and the right shape, what ends up happening is our orbitals start to combine. And they start to make something called hybrid orbitals, or hybrid molecular orbitals. And this can be a tough idea to kind of wrap your brain around, but it's actually pretty simple when you start to look at it. So down here you can read what hybridization is. It's the mixing of the atomic orbitals sp and d in an atom to produce a new set of orbitals which are better arranged in a proper shape to allow the molecule to, or allow that atom to bond and make a molecule that has the shape that we would expect it to, like we've been learning with the electron geometry and the molecular geometry. So for that carbon that we were talking about, its ground state electron configuration, remember, was right here, 1s2, 2s2, 2p2. If it gets excited, it bumps up that electron, so now it has four places to bond. Right here, right here, right here, and right here. But those, remember, weren't in the proper shape. So what actually would happen is that 1s orbital would stay alone. It would not have anything change about it because it's not a valence orbital. So the 1s orbital stays as 1s2. But the 2s orbital combines with the 2p orbitals. And it makes four special orbitals here. And those four special orbitals are called Sp3 orbitals because it's an S combined with 3p orbitals. And those Sp3 orbitals would be in the shape of a tetrahedron, a tetrahedral, the shape that we know that carbon likes to form when it makes four bonds. So hang with me for a minute. I know that this is really difficult and kind of tough to figure out at first, but once you start going through practice problems, it's not too bad. But basically what we're going to do is we're going to look at the number of electron domains around the atom of interest, usually the central atom. And the number of electron domains is going to tell us how many orbitals are combining. And based on that, we're going to be able to figure out what the hybrid orbital is going to be. So we can get any number of s, p, and d orbitals combining. So the first situation we can have is we can have what's called an sp orbital. An sp orbital is, whoa, watch this, two orbitals, one s and one p orbital combining. And what shape they make is this shape right here, aka linear. The second one is called sp2. It's one s orbital and two p orbitals combining. So what you end up with is three total sp2 orbitals. Those are for any molecule or any atom that has three electron domains around it. And what you end up with, the shape, is this is what sp3 orbitals look like. And that shape is trigonal planar. We already did Sp3. It's up here. It's 1s combining with 3p orbitals to make 4 Sp3 orbitals. If you notice, they're starting to add up. 1 plus 3 is 4. That's for any atom that has 4 electron domains around it, and it makes the shape of a tetrahedral. And then we can have 5 orbitals. If you have 5 electron domains around it, we know the shape is actually trigonal bipyramidal. That got cut off. I think it's on your paper. That's 1s combining with 3p orbitals. Well, we're out of p orbitals once we use all 3p orbitals. So remember SPD, there's 1s, 3p's, 5d's, right? So if you combine 1s with 3p orbitals and 1d orbital, now you get 5 orbitals called sp3d. So you end up with 5 sp3d orbitals. And guess what they're shaped like? You guessed it. They're shaped like trigonal bipyramidal. And going here, the last one that you can end up with is you could end up with 6, oops, I'm moving it wrong. You can end up with 6 electron domains around the center atom, and that would be 1s orbital combining with 3p orbitals and 2 d orbitals to make 6 sp3 d2 orbitals. And those sp3 d2 orbitals are going to look like a tetra or an octahedron. Alright? And so again, these hybrid orbitals are simply ways that we can combine the atomic orbitals so that they can bond in the proper shape, the proper molecular geometry shape. So here's a little step of how you do things. When you're solving these problems or figuring out hybridization, you simply draw the Lewis structure, figure out the molecular geometry, and based on the number of electron domains in the center atom, you know you need that many orbitals. If you add up the superscripts on the orbitals of the hybrid orbital, like sp2, 1s plus 2p's, that tells you how many electron domains total you should have. So 1s plus 2p's, sp2, means you should have 3 electron domains around your center atom. So let's run through 2 quick examples, and then we'll send you off and see if you can do it on your own. So there's the Lewis structure for BF3. If you look at BF3, it has 1, 2, 3 orbitals. Or sorry, 3 electron domains around it. So since it has 3 electron domains, we're going to need to combine 3 orbitals. So there's 1s that we could combine, and the other 2 orbitals that we're going to combine are going to be p's. So this molecule would form sp2 hybridization, which means it's going to look like trigonal planar. Right? Right. And so here is CO2. CO2, it has 1, 2 domains around it. I don't know what's going on there. It has 2 domains around it. So you need 2 orbitals to combine. So 1s and 1p orbital. So CO2 would have what we call sp hybridization. And it's going to look linear. Go ahead and try NH3, hit pause, try it, and then when you're ready, hit play again, and I'll have the answer up on the screen for you. So if you remember, lone pairs actually count as an electron domain, just like double bonds only count as 1 electron domain. So NH3 actually has 4 electron domains around it, so it needs 4 orbitals combined to make its hybridized orbitals, 1s and 3p's. So it's going to be sp3 hybridization, which makes this basic shape a tetrahedral. And of course that top one would have a lone pair, so its actual molecular shape would be trigonal pyramidal. Alright, I know that was a lot to throw at you. I'm sorry I couldn't be there to help you guys today. Do your best with what you can. Use the book to help you. And I'll see you guys when I get back on Monday.